Good afternoon, everyone. Today we're going to speak about sample pendulum. The experiment aims to determine the gravity constant G using a simple harmonic motion. First of all, we need to observe a simple pendulum motion. If you're just having a motion in this way, which is a simple harmonic motion with a small amplitude, trying to decrease the length, we will find it move faster. So the periodic time or the time needed to make one complete oscillation for this motion is decreasing. So as long as you decrease the length, you decrease the periodic time. So the relation between the periodic time and the length is directly proportional. While using a mathematical derivation for the periodic time and the length, we found that T equals to 2 pi root L over G. The T stands for the periodic time, which we mentioned is equal to the time needed to make one complete oscillation. And L stands for the length of the pendulum, which starts from the hanging point till the middle of the ball. So what about the G? Well, when you start a simple harmonic motion, it keeps go back and forth. So for this, we do have some kind of force affecting our pendulum. We need to know what is it, because there is no motion without force. By analyzing the motion, here we have the stationary position, and right now we are making angle theta, which we start the simple harmonic motion, and the other one, which goes back and forth. So we found here, for the simple pendulum, we do have a metal pole hanging at the end. So by this metal ball, we do have a mass on the negative y-axis. So by resolving the mg on the direction of the string and the perpendicular to the string, we found that here is the axis. We found here that this is the same theta we do have for the simple harmonic motion. And here we do have mg cosine theta as a force pointing down, which is not affecting the simple harmonic motion. But here we do have in the same direction of the simple harmonic motion, mg sine theta. So the resolving perpendicular component for the weight is what creates the simple harmonic motion. So here we do go back to the equation. Here we see that T equal to pi root L over G. When we need to make a relation between T and L, we can find this T square equal to 4 pi square L over G. So we can make a table using the T and the T squared and L. But remember, if you're using this experiment in your real life, you'll find some kind of obstacles, such as if you're making a oscillation, after a while, the amplitude of the oscillation decreases, okay? So this is because of two causes. Here, we have air resistance and we have friction at the hanging point. So due to the friction with the air and the hanging point, the amplitude decreases, which will affect, consequently, the periodic time. So in order to find an average for the periodic time, we need to take it for a while, such as make 10 complete oscillations. For an example, if you're trying to illustrate how a complete oscillation occurs, we start from here. When it comes back to the same position, the time it needed to move from this position back again is the periodic time. So in the table, we need to add the column for 10 oscillations. Okay, so for some reason, I'm going to tell it to you later, we have started from length 0.45, moving 5 centimeters each time. We need 5 points to make a straight line. So we started from 0.45, counting 1, 2, 3, 4, and 5. We stopped at 0.65. Okay? So if we are going to use our stopwatch here, Let's see how it works. We see here that we have the start and the stop button, and here we have the reset button. If you want to start something and then you want to stop, so by reading this time, it's 2.30. So it's 2.30 seconds. There's no O is placed because this represents hours, this represents minutes, and this represents seconds. If you want to reset the stopwatch, you just press reset. Okay? So, first of all, we're going to measure the length. Here, we're going to put it on 45, which is right now placed from the middle of the ball to the middle of the hanging point. It's 45 centimeters. Okay? Start the stopwatch when you have started the motion of the simple harmonic motion. Okay? So you're going to count 10 oscillations and then stop. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is the time for 10 oscillations. Remember, while I'm making the simple harmonic motion, I made it with a small angle, not with a big one. Because if you're trying to make it with a big one, you don't have the angle over here, because you're going to have a small periodic time. So the angle affects periodic time. In order not to enter the angle in our concept while doing the simple harmonic motion, we need to make it small. So for mathematics, we do have, if the angle is too small, the sine theta equal to theta. So if the angle is less than or equal to 10 degrees, we can ignore it in the relation and keep it in this way. So in order to measure it while making the experiment, you don't need a protractor. You just don't need to get out of the base. So here, how you make a small angle. Look at the vertical. It's a small. Okay? So back again to the time. We have the time 13.24 as I showed you before. So here is the time 13.24. Okay? In order to find the periodic time, which equals to the one complete oscillation, the time for one complete oscillation, we here have the time for 10 oscillations. We divide by 10. If you made it for 20 oscillations, you have to divide by 20. So here we say that T over 10 or T10 over 10, which is equal to 1.324. We square it to find the value of T squared. We need to repeat this for 0.5. I'm going to have the ruler. I need to start over here. Let's see. Yes, it's 50. Okay. So I'm going to reset and start my motion. Small angle. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right now, I get a time for 13.99. So here, it's 13.99. So to divide it by 10, it's going to be 1.399. Okay? So you have to repeat it from 0.45 to 0.65 in your lab. For a reason, I had started with 0.45. Let's see if you have a small distance, just like this one. Okay? If you're trying to make oscillations using a small distance, Due to the motion of the Earth, you're going to have two-dimensional motion soon. So you cannot finish your 10 oscillations while you do have two-dimensional motion, which is not good for our experiment. Our experiment goes for only one-dimensional motion. So the small length cannot work for us. Another thing you need to know, while you're trying to make the oscillation using a small distance, you can find that you can determine either it's in your direction or in the other direction. The counts for the cycles or the oscillations cannot be much more accurate. So in order to avoid this, we are trying to do it at 0.45 meter. Okay, start here, 0.45 meter. Okay, so this helps us to be in one dimension. So for an example, if while you're making your experiment, you do have a two-dimensional motion, you should stop and start again with one-dimensional motion, moving in one direction. Okay? So what about just having 5 centimeters between each? Why I cannot have about difference about 2 or 3 centimeters? Look at the time. If you have 13.24 to 13.99 as a difference for 5 centimeters, imagine how it's going to be for 2 or 3 centimeters. If you do it for 2 or 3 centimeters, the difference is going to be so much small, which will allow the relation to be, if you're trying to draw it in this way, it's going to make the relation in this direction. Points on the same axis, parallel to the x-axis, which is not suitable here. If you're trying to make the length 0, you can find the periodic time to be 0 also. Okay? So this is not how the graph should be drawn. So I cannot have 5 centimeters. So here, straight line passing through the origin. As we mentioned at the introduction, we do have points which is not going to be perfectly on the line, but around. So that's why we're taking the fitting line or the best fit. Okay? So remember that we had mentioned after drawing the line, you need to take the slope out of the data because each point in the data is having error. Okay? So while drawing the slope here, which is equal to t squared over L, looking backward at the equation, we can find that t squared over L equal to 4 pi squared over g. Due to our work in the experiment, we can find that the slope is equal to 4 pi squared g, but this is not a regular g. This is the experimental value for the g, the experiment you have done. So in order to find the g experimental, which is equal to 4 pi squared over the slope. So here you deduce the g experimental, the gravity constant experimental, which is required from the aim, and a given value for the theoretical g equal to 9.81 meter per second square. You have the experimental value, you have the theoretical value, so you can find the error. The error equal to the absolute value to avoid the negative sign, because there is no error with negative, the g theoretical minus g experimental over g theoretical. Multiply 100. So, as a review for the experiment, we have noticed that the relation between a periodic time and length is directly proportional due to the increment in length causes an increment in periodic time. Then we try to find why a simple harmonic motion can actually occur. So we analyzed the forces acting. We found that the weight can be resolved in the direction of the string and perpendicular to it. And we found that the perpendicular component of the weight causes the simple harmonic motion. So we go back to the equation while we have been driving it mathematically, which you're not required to do it by yourself. You just use the law. So t is equal to 2 pi root L over g. Taking the square for both sides, we found that t squared equal to 4 pi squared L over g. Due to the effect of the circumstances in the lab, like air resistance, friction at the hanging point, for an example, we can find that the periodic time is not going to be constant on all oscillations. So we need to take it for a period. We try to take it for 10 oscillation, which is enough period. Okay, we started the length from 0.45, moving till 5 centimeters each time till we reaches the 0.65. The time for the 10 oscillation is 13.24, which we have done it. It might be different in your experiment at the lab. You should try it yourself. Okay, so the periodic time is going to be the time for 10 oscillation over 10, which is equal to 1.32. Here we tried for 50 centimeters or 0.5 meters, which is equal to 1.3. The whole table, you should try it in your lab experiment. Okay, so we tried to draw a relation between the t square and L. Don't forget about the units, second square and meter. Okay, we draw the point, which is not perfectly because it's experimental value. So it's not going to be perfect on the line. We draw the slope and take 2 points on the slope from the line, not from the data. The slope equals to 4 pi square over g experimental. The g experimental goes for 4 pi square over the slope. We found that the g not theoretical equal to 9.8, which it's given. So we tried to find the error. The error shouldn't be more than 10%. Make sure you do not do a human error while you're making your experiment. For an example, you make a wrong measurement using the ruler. Not, for an example, if you're just doing the 45, you make it 47 or 45.5. This will affect the time and is not accurate. Try to make it accurate more. The time reaction, try to make it fast as much as you can. For me, right now, I do have a time reaction. Oh, I had a sort. Okay, right now I do have 0.43. You might do better in the lab. Okay? Thank you.